Hello everyone. In this paper we look at the following convex optimization problem. We want to minimize f of x such that x is a real n times n symmetric matrix which is positive semi-definite and with trace equals 1, and the function f is assumed to be convex and smooth. Now this convex optimization problem is a very well-known and highly popular convex relaxation to many low-rank matrix recovery problems such as matrix completion, phase retrieval, robust PCA, and more. And this convex relaxation is well motivated both in terms of empirical evidence and from a statistical theory perspective. The computational bottleneck in applying first-order methods to solve this kind of relaxations is the following. Such methods either require a full-rank SVD on each iteration to compute the projection onto the feasible set, which takes cubic time, and or to store high-rank matrices in memory, which require the square n memory. Let's take a closer look how using projected SGD on this problem looks like. So on each step, we update our current iterate by moving in the opposite direction of an unbiased estimator for the gradient, which usually is calculated by mini-batch. So here we denote this stochastic gradient by a hat of a nabla. And then we project the result onto the feasible set. And we denote the projection by capital pi. So for our feasible set, the projection takes the following form. We compute the eigendecomposition of yt plus 1. We project the eigenvalues onto the unit simplex and then just multiply from the left and the right by the eigenvectors of the original matrix yt plus 1. Okay, and here we see why we need the high-rank SVD to compute this full eigendecomposition. And here is a very simple heuristic to cut down on the computational demand of this method. What if we replace the accurate full-rank projection with just a rank R approximation, which we denote by a capital pi hat with a superscript of R? And this rank R approximated projection is simply doing the original projection, but only on the top R components in the eigendecomposition of yt plus 1. So instead of computing a full rank eigendecomposition, we just compute the top R components, which of course is much faster, and then we just project this onto the feasible set. And simple question, when can this heuristic provably work? Okay, so we can ask, when does this approximated rank R projection exactly equals the correct possibly full rank projection? And here is a starting point, so we just can understand why such a thing can be reasonable. Recall that from the first order optimality condition, the projected gradient mapping at the optimal point is just the optimal point itself. So if the optimal point is rank R, then the rank R approximated projection step is just the same as computing the correct projection, as long as we take the SVD parameter R to be at least that of the rank of the optimal solution. So can indeed we use low rank projection? So in this paper, we assume a strict complementarity assumption on the optimal solution X star. And this strict complementarity assumption takes the form of an eigengap in the gradient vector at the optimal point. So we denote this parameter by delta. And it's just the gap between the smallest eigenvalue of the gradient vector at the optimal point and the n minus r eigenvalue at the gradient of the optimal point, and we assume it is bounded away from 0. Now, why such an assumption should hold? Well, we can show that it is in fact necessary for the robustness of rank of optimal solution to small perturbations in the problem. See the lemma in the paper. And we also observe this in practice. what we can show is that under this strict complementarity assumption, we can draw a ball around the optimal solution, and the radius of this ball actually scales linearly with the strict complementarity parameter delta. And inside this ball, with high probability, the rank R approximated projection is exactly the correct Euclidean projection as long as the parameter R is at least the rank of the optimal solution. So if the optimal solution is of low rank, as we assume in low rank recovery problems, then inside this ball, we don't need to use a high rank SVD, only SVD of rank equals that of the optimal solution. We then use the standard martingale argument to show that once SGD is inside this ball, with high probability, the iterates do not leave this ball, so this property remains throughout the run. This brings us to the main result of the paper. What we show is that if SGD is initialized within this ball, which is the term for the radius is given in blue here, so it scales linearly with the strict complementarity condition. So if we initialize the SGD in this ball and we use a certain mini batch size and step size, which are given in the paper, then with probability at least 1/2, we have the original guarantee of SGD for this problem, the same convergence rate up to an additional log t factor. And moreover, all the iterates produced by SGD have rank at most that of the optimal solution. So SGD only manipulates low rank matrices throughout its run if with high probability if we indeed initialize in this ball. As a simple corollary, we have a sample complexity, again from this warm start, that as you can see is optimal up to logarithmic factor in terms of epsilon and the bounds on the gradient, the bound on the norm and the variance. And one more important thing is that in fact we can actually validate if the approximated projection on each iteration is indeed the correct projection. So we can actually validate if the algorithm converges correctly. And this can be done if instead of using a rank R star SVD on each iteration, we use a rank larger by 1. So use a R star plus 1 SVD. We also have some empirical evidence to show that this kind of behavior is not just theoretical, it seems to also hold in practice. So we have some experiment with the well-known matrix completion test. We use the movie length 100K dataset. Each one of the graphs here that you see corresponds to a different bound on the trace, which translates to a different rank of the optimal solution. And basically what we see here, in blue we have the convergence of SGD with low rank projections, and in red we have SGD with standard projections, and we measure the error versus the running time. Now, for both SGD variants, we use a very simple initialization scheme. We don't use any sophisticated initialization, just a standard simple initialization. And what we see is that SGD with low rank projections converges right from the beginning with correct projection. So each time we compute just a low rank projection using a low rank SVD, and it turns out that it is the correct Euclidean projection, just as if we have used the full rank SVD. And we also observed that in all these experiments, we have more in the paper, the strict complementarity condition indeed holds. Okay, see the paper for more details. Thank you for listening.